presentation, we want to learn a little bit more about recurrent neural networks, or RNNs, as well as long short-term memory neural networks, LSTMs. So let's start out with RNNs. So these are recurrent neural networks, or a recurrent unit. And what it does is it has a loop back to itself. So the input to this unit is the input vector, as well as its own state, if you wish. So that's why we have this thing. It's able to maintain its own state. And this is an idea that actually has been around for quite some time. So what we can do then is we can sort of like unfold this unit in time. So we see, some input vector at time t-1, a prior state, which might be a random state from initialization, and an output that we produce. So we have an input matrix U, an output matrix W, and then a matrix V over here. So then at time t, we have an input over here, our input matrix U, output matrix W, and then the matrix V from the hidden states that potentially come from other units also. So that's the big idea. It's just a hidden state that we then maintain. They're used quite a bit in processing language and speech, where you have variable inputs. If you think about images, they're kind of like, certainly if they're normalized, they're the same size. And so you can run those things through CNNs very easily. But language, it just really doesn't make sense to to normalize it. You might lose some information there, which would not be a good thing. So also, if we take not just a single sentence, but a piece of text into consideration, we have pretty long sequences of inputs. So that's the benefit of RNNs, or that's where we use RNNs quite a bit. You can't really talk about natural language processing with neural networks without talking about word embeddings. Let's do a little bit of a detour here to word embeddings. Basically, a word embedding is mapping a word into a very high dimensional vector space. So 200 to 300 dimensions is certainly not unusual, even 500. So the idea then is each word is mapped into this vector space, and as such is represented by a multi-dimensional vector. So the word dog might be mapped into this huge vector of 200 dimensions. So what are we going to do with this stuff? So these are, by the way, these are the inputs then. We'll see some slides later on that make this a bit more obvious. So what are the benefits of some of these things? So here is one of the applications that we can use, for which we can use these embeddings. This is a visualization of terms that are related to numbers, actual numbers, written out numbers, even some quantifiers, logical quantifiers if you wish, many, all. And this is just a portion of a visualization of this vector space, but they also are grouped together. So that's kind of pretty cool. So what people then did is they did this for English, and they did the same thing for Chinese. And this is an overlay of these two things. And well, I don't know any Chinese, but based on the fact that they show up differently, and based on the fact that it was a paper that was published at Stanford University, I imagine that these are kind of like similar words in these similar languages. And so that's obviously quite useful in language translation. Another useful application of these word embeddings is for paraphrase detection. So the idea then is that, again, this is a different excerpt of this visualization of the multidimensional space. So maybe you hear the word planned in a document, and you want to figure out how close is it to expected. And so based on the fact that they're very close in the vector space, you might reasonably infer that, these are very close in meaning. As opposed to, say, planned and ended, which are a little bit further away, so probably not as close. So that's another application of these word embeddings, like a direct application of the word embeddings. So let's move on a little bit then. I wanted to show you, this is a simple feed-forward network, so we're not doing RNNs or LSTMs quite yet. But I just want to show you how we use the word embeddings. So there's some text over here, hole in the ground, there lived. And so similar to as we have seen this thing for net talk, we look at a window of words over here, the ground here. And so these are the embeddings, right? So it's this huge vector. And then the is this word over here. This one is the embedding for this word over here. And then again, this is just a feed-forward network. And we have some hidden layers, which was an output. And the objective of the output is to predict, in this particular example, the next word. Okay, so that's again use of embeddings and use of feed-forward networks to predict the next word. Now here is the same thing, except we're using a recurrent neural network. And we'll say more about recurrent neural networks in a moment, but this is the RNN layer over here. We have an input word. In a hole, we have the embeddings, and we run it through the RNN. And so we again want to predict what's the next word. So we have seen the prediction task, which is one of them. Here's another task with RNNs. So we run the RNN. Again, we have this long piece of text, maybe an email, and we want to determine whether it's spam or not. So we do some processing, and then eventually we run it through a classifier. So this is a regular feed-forward network that eventually tells us, yes, it is spam, or no, it's not spam. Or, well, it's that's what we want to know, right? It's not like it's mostly spam. So those are some tasks that people are interested in, or for which they use RNNs. So let's have a look at RNNs in detail then. So as we know by now, is that neural networks have weights, and that we adjust the weights as part of wrestling those neural networks into submission. So let's see what's new when it comes to recurrent neural networks. So over here we have a single RNN unit. So the dashed line is, the output is being put back onto the unit, and so there's a weight associated with it, right? Just like there's a weight associated, or a weight matrix associated with this one, and a weight matrix associated with this one over here. So if we have input for more than one unit, then of course there will be another weight matrix associated with this. So here is a different image that sort of like takes much more of a view of the weight matrices, that sort of like visualizes them a little bit better. Again, as before, we have an input vector xt. We have a weight matrix. We have a hidden layer ht, and we have an output layer yt. Again, if we have more than one output, and we have the weight matrix v that goes from the hidden layer to this one over here. Now again, we have the hidden layer to produce the output, but again, remember we have the hidden layer also going back to itself, and again we can go back to other units, so we don't just sort of like go back to ourselves. But in this particular example, since these are the same size, this weight matrix U is just for each unit updating its own self with its own input. What we have over here is we sort of like draw it out in time, right? So in time step ht-1, we have activations. We have the activations of these units. And so we have this weight vector u with which to process this input. Long story short, we know how to adjust v, we know how to adjust w. So now we need to talk a little bit about, okay, what to do with u, with this weight matrix, because if there's a weight matrix, there's information or knowledge, it has to be adjusted. Let's see. So yeah, u, again, in this particular example, is just ht to itself. So what we have over here, so like to lead up a little bit to the training aspect, we unroll this network in time. So we have input 1 that is being presented. We process the information, produce output at the hidden layer, output at the output layer. And then next time around, next task, we present a different input, x2. We again have run through the weights. But now notice that at the hidden layer, we still like make this a little bit more obvious. We use the output that was produced in the prior time step that was sent to the output layer, but it now also gets sent to the next time step. So that's what we have over here. We use both of these pieces of information to produce a new output that we send on, and then again, obviously, to the next time step. So then how do we deal with the training over here? So let's start up in the upper right corner, which sort of like gets us to an area that we have seen before. So what we have over here is we have the target vector, which is the desired output. We do our subtraction, differentiation, and we have an error. We use this error to adjust the weights like we have seen before in backpropagation. All right, good. But what we really need to do is we need to look at what happens with the weight u, right, and how to eventually update it. So what we really need to do is when we update this thing is we don't just sort of like need to know about the error that was produced at the output layer. We also need to know what was the error at the hidden layer, right? So in other words, eventually we need to update u, but we also know to update h2, we need to know the error that came from ourselves. So not just from the output. And so that's kind of like what this one here portrays. We need to look at the sum of the errors produced by this one and by this one. So long story short is we add the error from the current output, but also the error from the next time step. All right, so moving on then to, sorry for this break, to LSTMs. Why are we interested in those things? RNNs are pretty powerful, but they have drawbacks. And the drawback is they're not very good at handling context or information that was presented immediately before or quite a while back. So let's have a look at the statement here. The flights the airline was canceling were full. Okay, so we might be interested in, so what is was referring to, what is were referring to, right? So was the airline, so the airline was canceling from flights. I'm sorry, the airline was canceling, but what does the were refer to? And so it refers to the flights, right? So this is much earlier. And so for reasons that we'll discuss here in a moment, the RNNs just sort of like have a hard time processing this thing. So what we need to do is, for LSTMs, we need to add some context. Again, the RNNs do carry state information in the sense that they can remember information that may be useful. We have shown that over here. Okay, where we have some, well, let's go to over here, where we sort of like push in some information, or that we keep some information that that might be handy to predict the next word. So predicting the next word depends on the prior few words, so that's not a big deal, right? But the challenge for those recurrent units is they need to provide data for the next task, as well as if we want to go back to this task over here, for tasks that are later on. So we might want to, one way to look at it is, in order to process this one over here, we sort of like need to do something with flight so that we can remember it when we're over here. Okay. So it's easy to remember things that just immediately happened before, but so this long-term relationship, that's sort of like hard to maintain. From a more technical perspective, like remembering the task of remembering of things that happened earlier has to really deal with propagating errors back through time. And the thing is that eventually we have a multiplication in this thing. And as you know, when we multiply things, small numbers less than 1, they get to be smaller and smaller and smaller. So as we do the backward pass training, this repeated multiplication eventually leads to what people call the vanishing gradients problem. So we're sort of like, in essence, lose information that we might want to keep. So to address this thing, we will, let's see, where were we? We will maintain what is called context. And so that's kind of what we need to explain here in the next couple of slides. And so the idea is that we explicitly try to maintain information that we might need later on. So it's a separate layer, if you wish. So we have now 2 inputs to a neural network. It's the data that is typically pushed through the network, as well as context data that is maintained by the network. And so these LSTMs are designed to manage which information is no longer needed, and so we will remove that, and which information maybe we want to add to the context layer. And of course, we don't want to hard code this stuff, so we want to be able to learn this stuff. And in order to learn that and to manage it, we have what they call gates. And so these gates are implemented through the use of additional weights that operate on the input, the previous hidden layer, and the previous context layer. So without much further ado, here's an example of an LSTM unit, again, in time. Time minus 1, time plus 1. So what we have is we have the input, we have the output. Okay, and the output also is obviously the same as the hidden state. But what we have additionally, we have this additional input that is the context. So again, this is the hidden state information, and this is the context information. Again, you notice that they're sort of like split over here. So again, as with recurrent units, input, hidden state, output. But now we have this context. So in order to deal with that, people use terms from hardware, and they're called gates. So there's this really great blog entry that has all these great images that I'm taking from it, and I'm acknowledging that I'm doing that over here. So we're going to zoom in a little bit and talk about some details. So first of all, a few things. So here we concatenate something, 2 vectors, so like one after the other. Over here we copy things, so just make a duplicate of it. Over here we just move information, and then over here we have pointwise operations. We have 2, multiplication and addition, and then we have the neural network information. So we have 3 different sigmoid functions, and then a tanh function over here, and a tanh function over here. So let's have a look at it. We are really interested in the context. So the context at time t minus 1 is, or from the prior unit, from the prior time step, is put onto this thing. We add things to the context, and then, we remove things from the context over here, and over here we add things to the context vector. So how do we do that? So what we do over here is, as we have seen, is we take the prior state and the input and we concatenate it. So we have a vector that's twice as long. But we run it, we do our usual thing. We produce the weighted sum of inputs, and we run it through a sigmoid function. As you know, the sigmoid function produces an output between 0 and 1. And so that's what this vector is here. It's a 0 and 1 vector. The interesting thing is how we treat this vector. We treat it like a mask. So over here, what we'll do is, well, let me go back to this slide over here. Since we're doing multiplication, anything that gets multiplied with 0 or close to 0 obviously gets removed. So if you remember a little bit from architecture and from your hardware courses, a mask determines which information to let through and which information to not let through, to forget, so to speak. And that's why we call it a forget gate. So the forget gate determines what information goes away, in essence, and which one are we going to keep. So that's it. So we now remove some information from our context vector. Next, we're going to look at the input gate. And the purpose of the input gate is to determine which information to add to our context layer. we have a similar operation as you can sort of see. We'll go to that in a moment. There's a multiplication over here. So we have a separate sigmoid activation function. Again, it's the weighted inputs, but it's a separate function. It's not the same as this one over here, that determines which values should we update. Okay, which ones over here we determine which values are we going to forget, which values should we update. And again, it's magic, right? No, we train networks, we train weights to determine that. As we will see later on, these take a huge amount of training, a huge amount of computing resources to do that. The 10H again produces an output in the range of -1 to 1, creates candidate values. Again, based on the input, the weighted sum of inputs, it sort of determines with its own separate weight matrix what might be some values that we for each of these for the vector, for each position in the vector. Now this one over here, then again, we're going to do the multiplication. Let me go back to this one. Let me advance to this one over here. And this one, again, acts like a mask. So of the values that this thing determined, we're sort of saying, well, I only want to keep some of these and not some other ones. And so that's what we have over here. So now we mask those values, and then we add them to the context vector. Okay? So this is additive. All right. So now we have our context vector is good to go. So the next step is to actually produce output. So now we're going to look at the output gate. And there are two ways to look at this thing. In the traditional way, we sort of say, hey, yeah, let me take my input, run it through sigma, and that's my output. But notice that the output is also the hidden state. So in the context of LSTMs, people don't really talk about output so much. They sort of frame this thing as the hidden state. So what of the hidden state do we need to know right now to process the current piece of information? That's really what we want to know. And that's what we're going to pass along to the next level of units and, of course, to our own state. So this is, again, we did all this great stuff with the context vector that sort of sets us up to process information in the future. But we still need to process the current piece of data, right? The XT. We'll need to do something. So what we do over here is we determine what of the context vector do I need right now? What do I need to send on to the output unit? And so what we do over here is we, again, this sigmoid function now acts as a mask. So before we saw conceptualize it as producing output, but now it again acts as a mask. And you know that because we have the multiplication over here. Now, we don't just take the straight context vector because of this addition over here. We may have values that are larger than 1 or smaller than -1. And so this one just squishes it. That's the only purpose of it. And so then we produce an output and we'll pass it along. So there you have it, LSTMs. On the next slide, I'm going to show you a different image that sort of emphasizes the matrices that are being used. And it's a bunch. And as you might imagine, the more matrices, the more weights that need to be learned. And that means the more computing time it takes to train the network. So again, it's kind of small, so I have a separate, it's kind of large, so I have a separate image for it. So as you can tell over here, we have, well, as you hopefully be able to tell, we have the input vector over here, we have the prior hidden state over here, and we have the context over here. They call the context S. So again, these are concatenated. You can sort of see that by this one over here. So we have this weight matrix for the first sigma function that they call F. And this is for the forget gate over here. This is multiplication. So we forget certain pieces of the input. Then again, this is a separate function over here, sigmoid function. As you know, we have a 10H function over here. Again, we use this sigmoid function as a mask to sort of determine the values that we then want to add to our context layer. So now we have our context layer, we pass it along. But before we pass it along, we also need to produce an output. Okay, so this is the context layer. And so over here we have yet another sigmoid function that we use. Again, we 10H this one over here to determine what information we're going to pass on. So pretty intense. Over here, it's a brief review of some of the units that we have seen. So here's a basic neural unit where we produce the weighted sum of inputs. We have an activation function, we produce an output. Then over here we have a recurrent unit where we're going to take the prior input as an additional output. Here we have the LSTM unit that uses 3 inputs to produce 2 outputs. And as I indicated, they are killers on CPU cycles. So people develop GRUs, which are sort of like condensed LSTMs, I guess. But we don't have time to look at GRUs. Take a neural networks course one of these days, and then so you learn more about that. Alrighty, folks, quite a bit of stuff to digest, so I will talk to you later. If you have questions, ask me. Bye.